going to be a lot of banging. The guys have arrived. Apologise for that. And we have a lot of delicate stuff to do here. I guess delicate's maybe the wrong word, but it's the first one that came to my head. We're going to do these basically word stories, related rates. And this is kind of where we left off the last one. Two boats, I think it was in the story, were 170 miles apart. Boat A heads east at 40 miles an hour, that's what that is. And boat B heads north at 25 miles an hour. And we're being asked to find the rate at which the distance between them, which I'm calling Z, so we're being asked essentially to find that number, dz by dt, and we're being asked to do it when X was 160, because 4 hours at 40 gives you 160, and Y was 100, because 4 hours at that. Basically, they said 4 p.m., but I just said 4 times that guy and 4 times that guy. So from this picture, I suck out this right angle triangle, which is very common in these questions. A lot of them have right angle triangles. And the reason I'm doing that is that we need an optimization function or formula, which is basically a formula that connects all 3 variables, and Pythagoras does the job. And then the next step, once we've got that, is to differentiate. This guy is going to be a chain rule. So it's 2 lots of 170 minus x to the power of 1 times the derivative of that, and that's negative 1 dx by dt. And y squared gets you the pretty straightforward one. And then finally z squared gets us that. So I'm starting just a little bit earlier than we did last time. Now, what you typically do next is plug in all the numbers. So I've got 2. I have 170, take away x, which is what, worth 160, multiplied by negative dx by dt, which is 40. So that's all that stuff, plus 2y, which is 100, times dy by dt, which is 25. And that's going to equal 2 times, oh, we don't know z, but we need to know it, times that. So it looks like we've got a little bit of a problem, and that is that when x is 160 and y is 100, we need to know z. So how do we find that magic value? How do we get z? I know x, I know y. Right, in particular, this version, right? So if you put in the numbers that we know, right, that's x is 160, this guy ends up being 10. And if you put in y is 100, do you see nice little Pythagoras thing going on there, right? And you could use it here as well. So what you've got is 10 squared plus 100 squared is z squared. That's 100. That's 10,000. And so the square root of 10,100, I'm not even interested in finding out what that is yet, because it's going to go in the calculator anyway. So 10,100. So next line, that guy's 10. That guy's 2. That guy's still negative 40. Should have fixed that earlier, but I didn't. That times that guy is 50. 50 times that guy gets you 5,000. And it's equal to 2 times the square root of 10,100 dz by dt. Now you multiply that, that's 10, that's 100, that's minus 800. Plus 5,000 equals all that stuff. So 4,200 because that stuff. Okay, what do I do to both sides to find dz by dt? That's where we are right now. What do I do to both sides?
Divide by 2 square root 2,100.
Well, that stuff agreed. And so 4,200 divided by, put a bracket around it, 2 times the square root 10,100. Probably need a couple of brackets. And we get about 20.9. And I believe the units were miles per hour. How do we feel about that? We okay? No problems? Right. Setting up these, especially the picture, to me is the crucial part of this story. Once you get that done, a lot of it becomes similar in many respects. So, that's question 11 done. Okay, let's talk about the next one, which is this one here I'm setting up. This is what it says in English, so I'll read out the question, because there isn't a picture. The altitude of a triangle, which I'm calling H, is increasing at the rate of 1 centimeter per minute. The area of the triangle is increasing at the rate of 2. So that's why that's there. And then at what rate, so find the B, the base, at what rate is the base changing? And then they go and they tell you when the altitude is 10 and the area is 130. So I've got a little picture, I've got a base. That's for the next question. I need a connecting formula, right? I need a optimization formula. Well, since they mention area and they mention base and they also mention height, does that seem reasonable? That the connecting formula is area is a half base times height. So now I'm going to differentiate with respect to t. Now in this world, the base and the height are both connected to t, right? They're both functions of t, which means that if I want to differentiate this, I'm going to have to do a product rule. So it's going to be f dash g plus f of g dashed. Now, if you differentiate a half b, you will get a half times dB by dt plus, I should say, times h plus 1/2 b times dh by dt. So that's the differentiation done. Now I know that that guy is 2, so I'm putting in all the numbers I know. I have a half. I don't know what this is, but that's because I'm trying to find its value. I know h is 10, plus I know 1/2. Looks like I don't know b, but I do know dh by dt. So there's one piece of this puzzle missing right now, and that is the value of b. Now I know h is 10, I know the area is 130, and now I need to find b. So you see there's a little sub job I need to do. And what I'm going to do is I'm going to start with the equation for the area of a circle. And I'm going to say, okay, if the area was 130 and the height was 10, then 130 has to be 5 times the base. And so there's my base, it's 26. Are you okay about how we found the value of b when they told us h and they told us a? We're good with that? Right. So now I can put in 26. So we have 2 is 5 times dh by dt plus 13. And now we've just got an equation. So I'm going to solve for dh by dt. And don't be worried about the negative number. That's okay. Right? Now, if you want to find dh by dt, you divide both sides by 5. And you get this rather strange answer. Essentially, does it not mean that the height of the triangle is shrinking, right? Isn't the height getting smaller, right? The base is getting bigger, the area is getting bigger, but the height is shrinking. So you can imagine a triangle that is getting long this way, but the height is coming down, right? So the total area does change, but it changes in this rather awkward way. Are we good with that one? Triangle formula, differentiate with respect to t, put in the numbers you know and find any numbers that are missing, and then solve. It's pretty much standard process for everyone that we've done so far. Are we good? Next fella. This is question 13. There is no picture to this. So this is question 13. So I'll read the story out to you. A boat is pulled onto the dock by a rope that's attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the boat. That's basically that line, and this vertical guy is a meter. If the rope is pulled at a rate of 1 meter per second, so if I call that X and it's getting pulled at 1 meter per second, you've told me that. How fast is the boat approaching the dock? I'm calling that distance Y, so you're being asked to find that. So find how fast it's approaching when Y is 17, when that number there is 7. Not 17, and that number there is. Okay, so we need to create a formula connecting the variables. And basically from that picture, can't you pull out a right angle triangle? And normally, the vast majority of the times, when you have a right angle triangle, isn't it going to be something to do with Pythagoras? So the connection here is going to be the x squared is y squared plus 1 squared. Now, the reason why I say virtually always is because of the next question. If it wasn't for that next question, I would have said, you always do Pythagoras. But we've got our equation. Let's differentiate. With respect to t, x squared gets you that guy. Y squared gets you that guy, and differentiating 1 squared is just nothing, so you don't need to write anything. Now, put in the values that we know. 2, well, it looks like we don't know x, so we're going to have to go looking for that. We do know what dx by dt is, and we're trying to find dy by dt. So it's this guy here, right? X. If I use my little triangle and I say, okay, I know that guy's 7. Would you agree it's just using Pythagoras again to get x? And to save a whole lot of time, can I tell you it's the square root of 50, but you can check it later. Does it seem reasonable, square root of 50 for x? So what do you do next? Well, basically, don't you just divide both sides by 2? And, well, that's a very nice answer. Square root of 50. And I forgot something. What did I forget? I forgot a y. There we go. Forgot my 2y, so that's actually 14. Well, I still divide, but now I'm going to get that answer. There we go. So draw a little picture of the information. Pull out a right angled triangle. That'll give me the relation. Differentiate with respect to t. Fill in all the guys' values, except obviously the one you're looking for, and solve. So there's one more of these left. Should always keep the best till last. This one breaks every rule that we've just done. Sure what I'm getting at. So let's read out this story to you, because it's kind of hard. It took me a couple of shots to figure out what they were saying. A straight light is 15 foot tall. That was easy. A man is 6 foot tall. And there's a shadow caused by that man. That bit I got. The man who's 6 foot tall walks away from the pole at the speed of 4 feet per second. So you can imagine that distance is x. What they just told me is that dx by dt is 4. And then they say, how fast is the tip of his shadow moving? It's there. So they're saying, find that guy. And you have to do it when x is 35. Oh, I shall just repeated myself there. Now, what you would typically do here is your optimization function would, in fact, you would think be Pythagoras, because almost every right angled triangle is that. But this is the one that breaks the rules. This is not Pythagoras. We are going to do a guy you've probably not used for a long time. Have some of you heard the term similar triangles? So similar triangles are shapes, triangles in this case, that are basically similar in shape. They're just different sizes, right? One's a bigger version of the other. Now, in this case here, the little triangle is a 6 by y, and the big triangle is a 15 by the total distance, which is x add y. Now, when you have two triangles that are similar in shape, as these are, there's a relationship between corresponding sides. And what that relationship is, if you take 15 and divide it by 6, you get the same answer as taking x plus y and dividing it by y. So similar triangles, I think it's phrased something like corresponding ratios are equal. Right? So the ratios of those two is equal to the ratio of those two. So there's your optimization function, right? Nothing to do with Pythagoras or squaring or square rooting anything. It's just based on similar triangles. Now, if you do a little cross multiply, 15y equals that guy. 15y is 6x plus 6y. If you subtract 6y from both sides, and then if you divide both sides by 9, you will get a very simple connecting formula. So I didn't differentiate that. That would be horrendously difficult. I did a little bit of algebra and made it pretty. So now my optimization function is that dy by dt is 2/3 times dx by dt, which is very simple. And dy by dt is the guy we're trying to find. And we know that dx by dt, we know its value is 4. And so the answer we get is 8/3. And you might say, I think quite reasonably, What about the 35? We never used it. And you might say, well, what about the y when x is 35? We never used that either. In fact, in this particular formula, it doesn't matter, does it? The answer never used them. So that tells me, so I've now got something to add to my useless pieces of information, that your shadow always runs at 8/3 if you're a 6-foot person. Which is why you can never catch your shadow. Isn't it going to be a little bit faster than you? It's always 8/3 feet per second more than you are. You ever seen little kids trying to catch their shadow and they get really annoyed when they can't do it? There's your reason. Your shadow's always going to be moving faster than you are, right? The tip of your shadow, you'll never be able to catch it. Unless, now I thought about it, unless you're on the equator, in which case the shadow is directly underneath you. Okay, that's me pretty much finished that section. So I've went through all the, or at least my versions of all the last 5 questions. Anything to add or ask before we move on then? So we are going to do our next section then. Yeah. Bear with me for a few moments while I get it set up. And our next section is 310. And it's linear approximations. Close some windows here so I can see what the heck I'm doing. So linear approximations and things called differentials. I'm going to give you some background before we get into the details of that. Today we're only going to be working on the linear approximation side. We'll probably finish that tomorrow and then we move on to differentiation, differentials I should say, and get them finished. So bang on schedule. Just waiting for some questions to go up. Yeah. We've used this diagram a lot, especially in week 1, right? Just a general function. Let's suppose I take this point here. And let's pretend this is x equals 3. I can find the slope of the tangent line and then I can create a tangent line, right? The green one. So far, so good. There is this is called the tangent line, right? And you can find the equation of the tangent line, right? You can find the slope of it. You can tell what the coordinates of that point are. You put the whole thing together and you get the equation of the tangent line. So we are going to give you a new name. And I'm trying to get the spelling here. The new name is a linearization, that I got another function. So I want you to think of a linearization function as exactly the same thing as the equation of a tangent line. Now this function called the linearization function, right? has lots of other names. Obviously, it's called the equation of the tangent line, which is probably the best name of them all, but this is another name for it, right? You will also see it in some textbooks called the linear approximation function, which is actually quite a good name when you find out what it gets used for. I think that's the most common ones, but linearization function and linear approximation function. In WebAssign, you're going to be asked using this. Right? Now, we very often will call it L of X, right? L for linear, right? So we are going to find a straight line, L of X, this tangent line. Now we could do it the usual way, right? Just find the derivative, plug in X equals 3, get the slope, Y minus Y1 equals MX minus X1, right? That whole process. Or you could do this. This formula is how you can find the equation of a tangent line at any point where the X coordinate is A, right? This is the linear approximation function at X equals A. This is the linearization function at X equals A. This is the equation of a tangent line at X equals A. So it's 3 names for the same guy. Are you just comfortable with different names for the same guy? So let's put that into practice. Let's actually find a linearization function. Suppose I take X cubed and I'm interested in X equals 3. It's going to be called A equals 3. That's how they would do it in the question. So I would find its derivative. I'd find its derivative, its derivative at 3, which is a rather unfortunate coincidence. It's 27. I'd find the value of the function at 3, which is also, by unfortunate coincidence, also 27. So the linearization function is f of 3 plus f dashed of 3, x take away 3. So in this case, it's 27 plus 27 x minus 3's. And you are expected to do a little bit of style points. Oh, yeah. 54. Yeah, 54. And there is our linearization function, our linear approximation function. And if you call that y equals, don't you also have the equation of the tangent line? So far, so good. So we are going to be looking at calculating, for no good reason right now, the linearization function. So let's give you a reason for why you would want to even calculate the equation of a tangent line. Let's go back to my picture here. Have you ever noticed that when you did Desmos, the tangent line and the curve were almost on top of each other in a lot of cases, that you couldn't really tell where the curve finished and the line started? I mean, eventually they drifted apart, right? But in a small window of the world, say in that window here, isn't the equation of the tangent line and the curve almost on top of each other? What that means is that we can use this guy, right, the value of this function, to estimate what the value of the real function is. And that's why it's sometimes called the linear approximation function. That's its main use. What it does is you can have a really, really ugly formula that's very hard to calculate. but isn't a straight line, which is what a linear approximation function is. Isn't that very easy to calculate? And if both answers are darn close to each other, wouldn't it make sense, you know, to make your life easy, to use the shortcut, right? So I'm going to try and prove it to you. I'm going to do a linear approximation function for sine x, and I'm going to do it at a equals 0. Well, the value of the function at 0 is the sine of 0, which is 0. If you differentiate sine x, you get cosine x, and the value of the derivative at 0, right, is the cosine of 0, which is 1. Right, we're ready to go then. The linearization function, f of a plus f dashed of a, x take away a. 0 plus 1 times x minus 0. Wow. The linearization function is really just the straight line y equals x. So if you did in Desmos the sine function, and you found the tangent line at 1, it would look something like that guy, wouldn't it? Would you agree that it's pretty close to the sine curve when x is close to 0? So let's see how good using that function is to that guy. Okay, 0 point. We're going to play a little guessing game. Vanessa, give me a digit 1 to 9.
Wait, for just any?
Any digit.
Okay, 6.
Okay. Santiago, give me another digit.
2.
Got a 0 there. Okay, 0.062131, right? I just added an extra 0 because I wanted it to be small. Now, according to this guy here, the answer is 0.06213, right? Because it's the same thing as the x value. Over here, of course, right? Over here, it's going to be the sine of 0.06231. Now, since we're in calculus, things should be in radians, so I'm making sure my calculator's in radians. Here we go. What would impress you? If this was good to say 2 decimal places, would that be impressed? Do you need 3 decimal places before you'd say, hey, that's pretty good?
4 decimal places.
Oh God, you're tough. Here it goes. Sine 0.06231, right? And the answer is 0.06209, which is 0.0621. We got your 4 decimal places, Vanessa, didn't we? If you round off. So if you lost your calculator, but you still wanted to know the sign of a nice small number, right? Don't do it for 42 radians, right? But do it for nothing point, 3 and nothing 0.07. Can you simply just get the answer and say, the sign of 0.06 is about 0.06? Isn't that interesting? We can approximate sign, and don't approximate it over here. Would you agree if you started using whatever that value of x is, wouldn't the answers be quite different, right? But as long as you keep close to 0, and that's all, the only restriction we have, right? Keep close to, in this case, 0, you are good to go. Try another one. Y equals the square root of x, okay? Now I'm going to center this guy at 4. Because square root of 4 is easy to do, right? So square root of 4 gets me 2. Right. If I differentiate this guy, well, that's going to take a bit of work. So here goes. Multiply by the power, reduce it by 1. Make it look pretty. And now you can plug in 4 and the derivative at 4 is 1 over 2 times square root of 4, which is a quarter. So we know the derivative at 4, we know the original function at 4. Apologize for the noises. Here we go. So it's going to be the value of the function, 2. The derivative, 1/4. X minus a is x minus 4. So it's going to be 2 plus 1/4 x take away 1. So it's going to be what? 1/4 x add 1. So far, so good. Right. So let's check it out. Since we are centered at 4, don't use this function here for the square root of 40, right? Use it for values that are close to 4, right? So 4 point something or 3 point something, right? That kind of number. Don't go crazy, right? So I'm going to use it to estimate the square root of 3.88. So according to this formula, 3.88 is 1/4 of 3.88. Have you noticed? Yeah, there we are. Plus 1. On my calculator, 3.88 divided by 4, add 1, ends up being 1.97. So we're essentially saying that we estimate that the answer is that. Okay. So far, so good. Some are better than others. I'm not going to ask you again because you're too tough. 4 decimal places was asking a lot. Santiago, you're much more generous. Would you be happy if it was at least good to 1 decimal place? Or do you want 2?
No.
No, what are you wanting then?
2.
I thought you might. Okay, so here goes. Not so confident on this one. The square root of 3.88 is 1.9697. Oh, we nailed it. Doesn't that round off to 1.97? Oh, come on, you got him impressed. That is a cool little trick. That you can take a function and just rewrite it as a straight line. And as long as you keep your values close to this number, the answer to this will be really close to whatever the original function looked like. I'm going to spend a few moments as soon as I get this set up. So while I'm doing that, why don't you do your attendance thing? Give me a few moments to do this. Okay, I think I'm ready. We've been, have I blocked you lot from chatting? Because I can't see.
It
Your
only
thing.
it says direct message to you.
Oh, okay, I was just playing about with it, so let me unplay about with that. Right. I'm going to have to close this. You know, you should never play about with software. I can't see your attendance. Okay, I can see them now. Phew, that was dangerous. Yeah. Well, that was close. Right, what I was doing before I confused myself is I was setting up Desmos. So here we go. We'll do the first one, which is y equals sine x. And we won't do it in capitals. Is what you'd expect it to be, right? And wasn't it y equals x? So let's zoom in. Right, the blue line is the linearization function, right? The tangent line. Would you agree it starts to drift round about a half? You see it? Zoom in there. Can you see it beginning to drift round about there, right? It looks to me like it is pretty decent at 0.4. Would you agree the gap there is only a little bit? And would you agree by the time you got to 0.3, nobody can tell the difference? Right, and if I zoom right in there, would you agree you can't tell where the red guy is and where the blue guy is? Isn't that because their values are identical, at least to 4 or 5 decimal places? Pretty impressive. The second one that we did then was the square root of x. Don't know why I need brackets, so I'll take them out. There's the square root of x. And the answer that we got for that one was what? 1/4 x plus 1. I'm just going to type that again in. There's 1/4 x plus 1. And zoom out, because we centered at 4. Right, you see at 4 the fit is good. Right, so when a is 10, the fit's going to be really good at x equals 10, right? That's where you should focus on. Now, if you look at the square root guy, it's pretty good, well, as long as you pick numbers, what, from 3 to 5? Zoom in a little bit. There. It's pretty good from 3 to 5, right? Not great. What about from 3.5 to 4.5? Would you agree you can't really tell the difference? Let's zoom right in. Although you can't see, that's about 3.5 and there's about 4.5. Have we convinced you that this little trick of using essentially the equation of a tangent line allows us a way to evaluate? It could be the ugliest function in the world. I just picked nice ones to make life easy, but couldn't I have done e to the x sine x over x cubed plus 1 all inside a big square root, right? Some really ridiculously ugly. Wouldn't it be nice if you could just evaluate that by using the line y equals 2x plus 1? I mean, wouldn't that make your life so much easier if you were only interested in approximating values? I think it's amazing. Right, so I should finish with a joke then. What kind of joke shall I finish with? Did I tell you about the Scotsman, the Englishman, and the American who worked in a whiskey distillery? No. Well, obviously in this story, that's where they worked. And they were working on some scaffolding, and the 3 of them fell into the vat of whiskey. And 2 of them survived, but the Scotsman get killed. So the manager of the factory phones his wife and says, you have to come in, there's been a terrible accident, your husband's been killed. So she comes in and she says, well, tell us what happened. He says, well, they were working on some scaffolding and it gave way. And, the other, the Englishman and American and your husband, they fell in the vat of whiskey, and the American, swam out and he was okay. And the Englishman, he swam out and he was okay. But your husband, he never made it. And she says, oh, that's terribly sad. At least he didn't suffer. I mean, how long did it take him to die? And the manager said it took him 6 hours. She said, 6 hours? I said, yeah. You know, it would have been quicker, but he climbed out twice to go to the bathroom. Oh, come on. Santiago, that's a good joke. No. Vanessa, is that one of my worst jokes? No. Is it just in the middle then? Okay. Right. Have a nice day, everybody. We will see you tomorrow where we will do questions like the one we've just done, but show you the way that WebAssign asks. And then we'll move on to guys called differentials. So see you tomorrow. I'll hang about